Hi, welcome. This is Dr. Shanzer. Welcome to the Atomic Structure Regents Chemistry Review. Hope you're having a good day. Let's get right to it. So before we begin, I just want to bring up a couple of things. You're going to be seeing me go in and out of the screen throughout this at times. And I wanted to just point out some information for you. So you will now see the in and out of the screen that I am referring to. Please excuse that. Okay, so here's our Regents review, and I am Dr. Shanzer. Now, before we begin, just so you understand, there is a way for you to communicate with me through Remind. If you text to 81010 and you text at LiveST, you will be able to get to me. I'm sorry, not at LiveST. You will text at Dr. M. Shah. This is a mistake. Please disregard that. This is the web address. If you're going to do it through your computer, this is the way you're going to text it. The PowerPoint that I will be using today will be available at this web address, and this is where we can find the schedule for the entire day's events. Again, disregard this. This is an incorrect image. This is where you want to be going. So let's get back to it. Okay, so when we talk about the chemistry regents, we're going to be going through the entire unit of atomic structure, and then we will actually go through the sample questions that I've included in the PowerPoint, some common things that you will expect to see. So I'm going to disappear in terms of my image, but you will hear my voice, and let's get right to it. Okay, here we go. Okay, so these are some of the questions that were submitted. What is the difference between ground and excited state? We will address that in the lecture today. What is an isotope will also be addressed. What do we have to know about intermolecular forces? That was one question. That will be addressed during the matter session as well as the bonding. The rest are about quantum theory, which is really SAT 2 level. You won't see anything about quantum theory in the region, so we don't have to worry about that. So let's start with the scientists. We can talk about Dalton being the first significant scientist, and his concept of the model of the atom was basically it was a solid sphere like a bowling ball. When we move further ahead to Thomson, he came up with the plum pudding model, and what we can recognize with Thomson is that the concept was it was basically like a positive sphere or cloud, if you will, that had negative charges embedded in it. So we're starting to see at this point the differentiation between positive and negative charges. Now Rutherford came along and by accident came up with the discovery of the nucleus, and we'll go into a little bit more detail in the next slide. From Rutherford, we can see that Bohr piggybacked on the Rutherford model and talked about the paths that the electrons travel in, which would be referred to as energy levels or orbitals. He did think of them as being clearly defined paths, as you can see over here, and sometimes it's referred to as the solar system model. The modern model, also known as the wave mechanical model or the electron cloud model, basically takes Bohr's model but determines that and this is the work of a lot of different scientists, not just Schrödinger. But what we can see from this final model is that the electrons are basically floating or orbiting, I should say, in clouds, not specifically defined paths as Bohr had thought. We can never know exactly where an electron is going to be located. We can know the most probable location. So these orbits, if you will, or energy levels that Bohr talked about, if you can imagine them being these general areas and clouds, that's where we're going to be finding the electrons. Now let's look at the Rutherford gold foil experiment. What we can recognize here is we have the laser beam, which is consisting of alpha particles, which is a positively charged particle. It's basically a helium nucleus, and literally was shot at a thin sheet of gold foil. He did this to not prove something new, but rather to support Thomson's model, and by accident discovered something that really changed the way we looked at the atom. We can see here from the picture that the atoms or the nuclei, I should say, are going straight through the foil for the most part, and this is what he expected. It's the ones that got deflected at angles or got deflected straight backwards. This was basically about 1 in every 20,000 that gave Rutherford cause to come to some other conclusions. And if we look at this, this is really a profile shot. These are representing 4 gold atoms, which would be part of the gold foil. These are your alpha particles. And what we can see here is that many of them are going straight through, which is what he expected. But when we see some being deflected at angles, large angles, or going backwards, this gave Rutherford cause to conclude that something must be causing that. And the conclusions he came to were twofold. One was that the nucleus was small, positive, and dense. And the second was that the atom is mostly empty space. So this big gold area around these positive nuclei is really representing the electron clouds. So when we talk about Rutherford's experiment, these were the 2 conclusions that he came to. And you will most likely see something on the Regents about Rutherford, because this was really a significant experiment that really changed everything about the atom. So small, dense, positively charged nucleus, and then we have our atom that is mostly empty space. Please, if you do come across a question where to ask you to explain something about the Rutherford model, please do not refer to the nuclei as being mostly empty space, because the nucleus obviously is the only place where there actually is something. Okay, so let's break it down and look at the anatomy of the atom. So here we have our nucleus, which is represented by protons and neutrons. And we can see here that a proton has this kind of notation. And remember, table O in your reference tables gives you a little reminder about that. Remember, this is the mass of a proton, 1 AMU or 1 U. And this is its charge, which is +1. Neutrons, we know, also have a mass of 1 AMU or U, and its charge is 0. You can see the word neutral in the word neutron. This is what makes up the mass of the atom. Outside the nucleus, we have our electrons, which have no mass for our purposes and a -1 charge. Now, what we want to take note of is this is the Bohr model. And although we know that there are not these clearly defined paths, this is a great image to help you as a reference point in terms of knowing the subatomic particles that are part of the atom. And I bring this up because I've noticed in the past some students have a little moment of anxiety or freeze up when they're asked to explain something in terms of subatomic particles. These 3 particles are the only subatomic particles that you are going to be responsible to know. Even if you've been struggling with chemistry, you know that there are protons, neutrons, and electrons. You should recognize where they are located and keep this image in mind. It will be very helpful for you as you navigate your way through many of the questions. Now, I want to bring up something because this is representing an atom. And we can see that this atom has 3 protons, and we can see it also has 3 electrons. And we'll talk about this a little later on. But what we want to remember is that an atom is electrically neutral. This means that the amount of protons and the amount of electrons will always be equal to each other. And we should remember that from the periodic table, we can look up the atomic number, and we know that the atomic number and proton number will always be the same. And if, again, it is an atom, electron number will also be that same amount. So let's get to ions. Because we talked about atoms, we should understand that ions are the result of a gain or loss of electrons from an atom. So if it's an anion, we talk about an atom that has gained 1 or more electrons to form a negative ion. Therefore, we know that the electron number has increased. If it is a cation, we understand that it is an atom that lost 1 or more electrons to form a positive ion. So we can recognize that this is going to help us when we are trying to determine the number of subatomic particles when the question is asking you to determine electron number. And this is what makes an atom and an ion different. Now, here's some terms that we should be familiar with. Atomic number, as I said, always is equal to proton number. And if it's an atom, like I said before, electron number will also be the same. We just looked at how electron number changes if we're talking about an atom or an ion, so we can understand that that number can change if it's an ion. Nucleons is another name for what's in the nucleus. And we've already looked at that simple Bohr model, and we can recognize that protons plus neutrons are considered the nucleons. And this is also what gives us our mass number, not to be confused with atomic mass, which we will talk about later on as well. Nuclear charge is literally the charge of the nucleus. And if we think about that model again, the Bohr model, we can recognize that there are protons and neutrons in the nucleus, and only protons have a charge, which is positive. So when they ask you about nuclear charge, they're really asking you to tell them about the number of protons. Keep in mind that it's always going to be a positive number. And finally, the definition of an atomic mass unit, also known as an AMU, also known as U. Sometimes that symbol will be used, and you'll see it on table D. And this is the definition: 1/12 the mass of a carbon-12 atom. This is one that you should sort of be familiar with. If you have to memorize it, but this one will come up sometimes. Now let's look at the notation format. And when we talk about notation, we're looking at the symbol, we're looking at the mass number, and we're looking at the atomic number. So if we talk about, this is sodium, and we can see that this indicates 11 protons. We know that that corresponds to the number, the atomic number as well, being 11. And since mass is consisting of protons plus neutrons, if we subtract those two numbers, we'll get our number of neutrons. Again, there's no charge being indicated here, which tells us it's an atom. So electron number and proton number will be the same. Now, if we look at this, now we have a sodium ion, and this +1 indicates that there is a loss of electrons. So what we want to remember is that if it's a plus charge, or positive charge, we do not add protons. It's about gain or loss of electrons. So a +1 indicates that there was a loss of electrons. So if we look at the information again, we can see that our proton number will be the same, however, and our neutron number will be the same. However, our electron number is what's different. And notice the +1 is indicating a loss of 1 electron, and we represent it this way. Now, there was the question about isotopes. So let's look at an isotope, another isotope of sodium. And notice that it is still sodium. Notice that it has a mass of 21, and its atomic number is still 11, because isotopes of the same element will always have the same atomic number. Its mass, however, is going to be different, because now we're looking at 21 minus 11. That's going to give us our 10 neutrons compared to these two versions having 12 neutrons. Electron number, again, is still the same because we don't have a charge indicated. So what really makes different isotopes of the same element different is their mass number. And if we talk about the subatomic particle that makes that mass number different, we should recognize that it's the neutron number, because proton number will never change. If it does, we've learned from nuclear chemistry that we've changed the element. Let's talk about electron configuration, basically showing us how the electrons are distributed in an atom. And if we look at this, here's some samples from your reference table. Notice we have the groups 1 and 2 and 16 through 18. And this sequence of numbers at the bottom of the box for each one of these elements indicates the electron configuration. So for lithium, we know with the first shell, we have 2 electrons, and then in the second shell, we have 1 electron. We can see something like chlorine, we have 2 electrons in the first shell, 8 in the second, and 7 in the third shell. And what we want to understand from this situation is the last number is your valence electrons. And these are important electrons because they're involved in bonding. And when we talk about ions being formed, excuse me, we should understand that these are the electrons that get affected. Now notice our group 18 are noble gases. Remember that they have 8 valence electrons. This is a full valence shell. And what we want to remember is that That's what makes them stable. And when atoms are losing or gaining electrons, they're either trying to empty the shell, like the metals over here, to be left with this full amount, or we want to look at these atoms here. When they gain electrons, they'll be left with 8 valence electrons. So this will give us the opportunity to recognize why these ions are forming. It's about stability, and ions are generally involved when we talk about the formation of compounds, which is why a compound will generally be more stable than the atoms that make up the compound. There's a little review for you. A little side note, little trivia question here. Group 17, the only group on the periodic table that does have elements in all 3 phases. I know Mrs. Mintz in the next session will be talking about periodic table. Let's talk about the Bohr model. So here's our sodium again, and notice its electron configuration. And the electron configuration is going to be important because that's going to help us with our configuration or drawing of the Bohr model. And just as a side note, I'm noticing some people are starting to join the Remind group. I will address your questions at the end of the presentation. So please feel free to send the questions through, and we'll go through as many of them as we can. So if we talk about having this number here, the sequence of numbers, it really is doing a lot of the work for us, because to draw a Bohr model for an atom, we can see that here's the nucleus, and we know that it has 11 protons. We know that it has 12 neutrons, which we figured that out already. And then you take your electron configuration and almost cut and paste it like this to represent the amount of electrons that you will find in each shell. And there you have a Bohr model for an atom. But you may be asked to draw a Bohr model for an ion. So let's look at the sodium ion. And we notice that it's an ion because it's a +1. And notice how the electron configuration changed. +1 means it lost 1 electron, and the valence shell is where we should be looking. So notice that we have no more electrons in the 3rd shell. So we're going to set up our nucleus exactly the same. We're going to put in our shells as they appear in the electron configuration. But remember that this shell is no longer possessing any electrons. The other thing we do need to consider is the fact that this is an ion has to be indicated with a Bohr model using the brackets and putting the charge outside the bracket. So this is a clear way to see the differentiation between an atom and an ion. Ground versus excited state. So we can look at this and understand that the ground state is when electrons occupy its normal energy levels. So when we talk about the electron configuration that appears on the periodic table, that is representing the ground state for all those atoms. Excited state is when 1 or more electrons jump to a higher energy level because some type of energy was being absorbed. Keep in mind, this is a temporary situation. It is an unstable situation, and those electrons will quickly return to their ground state. Now, to understand a little bit more about this, we want to think about energy absorbed is always going to be equal to the energy emitted or given off. Now, the energy that is absorbed by the 1 or more electrons could be heat, could be electrons, it could be a photon, which is light energy. And as you can see, what we have here is we have the situation where there is an electron in the first shell. Now, the excited state is representing that electron jumping to a higher level, as you can see here, because it absorbed energy. Now, when it returns back to its ground state, that's when you will see the characteristic color that is associated with that particular atom or element. And when we talk about the regents asking questions about this, we want to make sure, because this is something that over the years I see a little bit of a misrepresentation by some students, so let's hopefully learn from their mistakes. Electrons absorb energy, get excited, and go to a higher state. So they go from their ground state to their excited state because they absorbed energy. That is not when we see the characteristic colored light being emitted or released. It is only when the electrons are returning from their excited state back to their ground state, back to their original state. That is the moment when we will see the characteristic colored light. So please, if you are faced with a question regarding ground and excited state, which I'm sure you will be clear about how you answer the question. be sure that your answer is demonstrating that you are showing that the colored light or energy that is being released when the electron is returning to the ground state. That's really the way that you're going to get credit for the answer. It's not electrons absorb energy and then you see the light, the colored light. It's they release the energy that was absorbed, and that's when you see the colored light. Okay, so let's continue here. So here's ground state. And again, we're looking at our Bohr model, and we're looking at our electron configuration. Notice this is how it is normally going to be seen: 2, 8, and 1. Now, if we talk about looking at the excited state for the same atom, we can see that, notice, one electron left here and jumped to a higher level. You can have one, you can have more than one. And what we see is the Bohr model has changed. What we want to also recognize is that we did not gain or lose electrons, because here we can see that we have 2 and 8 plus 1, that's 11, which, by the way, electron number equal to proton number and atomic number because it's an atom. Now, if we look at the bottom excited state, we can see that something has clearly changed, because we know that the second shell can hold 8 electrons. And if we look at this, we can see that it basically had 1 electron jump to the 4th shell. But we still have 2 and 7 is 9, plus 1 is 10, plus 1 is 11. So we still have the same amount of electrons. So keep in mind, we don't gain or lose electrons. It's just a redistribution temporarily, and then we go back to our ground state. And when this electron goes back to this level, that's when we're going to see the colored light that is usually associated with these types of experiments. And you can recall, I'm sure you did a lab in school where you heated up some solutions. You also may have done something with gas tubes where you look through a spectroscope, or possibly some 3D glasses to see a colored band. And that brings us really up to the next part, which is the atomic emission spectrum. And when we look at the emission spectrum, we want to understand that it's really a series of bright lines produced when excited electrons are returning to their ground state. So it really piggybacks on what we just talked about. And what we want to understand is each element has its very own unique spectral pattern that can be used to identify if that element is present in whatever the situation may be. So if we look at this example here on this slide, we can see that we have 8 different elements. And notice that hydrogen and then helium, they don't have a lot of lines, but as we go further down, the elements are getting bigger and bigger, and some of them have the same colors, but none of them have the same exact pattern. And this is what we want to keep in mind, is that it's kind of like a fingerprint in the sense that every element has its own unique set of spectral lines. That's what these are, and they represent a particular pattern that is unique for only that element. And every element, like I said, has its own pattern. And if we think about, because a lot of times I'm sure students are saying, how is this going to be anything that affects my life? You know, I'm never going to see this. And in essence, you do see it a lot. When you see any kind of neon sign, this is a glass tube filled with neon gas, which is basically lots and lots of neon atoms, and electricity is being sent through, and it's just a constant excitation and then returning to ground state of electrons for every atom. So when you see a neon sign, you're looking at chemistry. Here, the xenon headlights, which are really bright, have a light blue tint to them almost. Different fireworks, as you can see, have different elements giving them color. Here's an example with sodium streetlights. And elemental analysis in space, on the sun and stars, also using a sophisticated spectroscope, which basically takes the summation of all the light and breaks it down into the colored bands, will give us the ability to actually talk about what is present in this particular sample that they may be talking about. Now let's look at average atomic mass, because this is something else that you will see. And we want to make sure that we don't confuse atomic mass, which is a decimal, which is an average, a weighted average that you see on the periodic table. We don't want to confuse that with mass number, because mass number is something different. So a weighted average of the masses of all the naturally occurring isotopes for that element. So a common question I see on the Regents multiple choice question gives a question regarding what atomic mass is, and one of the answers they talk about is the weighted average of the most abundant isotope. And what we want to understand here is that isotopes are occurring in nature, and there are different percentages of each isotope that will appear, some greater and some less. And we refer to that as their natural abundance. So when we look at this number on the periodic table, remember this is a decimal number, and that is always going to be an atomic mass. Mass number is always going to be a whole number because if we recall from the beginning of the presentation, mass number is about the sum of protons and neutrons. So we won't have a decimal number because we won't have part of a proton or a neutron. So let's talk about this relative abundance, or percent abundance as it may be referred to. Here's an example showing carbon 12, carbon 13, carbon 14, and we can see that they're all carbon, so they're all going to have the same number of protons, but the neutron number is what is going to be different with each. And as you can see, carbon 12 has the highest percent abundance, carbon 13 a very small amount, and carbon 14 even smaller. We're talking about scientific notation with a negative exponent. But the percent abundance along with the mass number for that isotope is what gives us the means to calculate the average atomic mass. And that leads us to this slide, calculating average atomic mass. So let's look at an example here. We have element X, and it has two natural isotopes. The isotope with a mass of 10 AMU, and notice how it's being represented, has a relative abundance, or it could be a percent abundance, of 19.91%. The isotope with a mass of 11 AMU has a relative abundance of 80.09%. Calculate the atomic mass of this element. Now in the Regents, you may be asked to actually calculate or just show the correct numerical setup. So let's go through the simple procedure that you need to do in order to come up with that. So here's the basic formula. So atomic mass is equal to the mass number times its percent abundance plus the mass number of the next isotope times its percent abundance. And notice I have dot, 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 because there doesn't just have to be two different isotopes. There could be three, there could be four, there could be five. So you just repeat this, and then of course we're going to divide by 100 because we're using our percent numbers. These numbers are out of 100. So if we don't divide by 100, we're going to end up with the wrong answer. Now if we plug in our information, we can see that there's the 10 AMUs times 19.91 plus 11 AMUs times 80.09. And when we do our math, we end up with a final answer of 10.8009 AMUs. You could also just use the unit of U. Now there is more than one way to set this up, but this is the easiest way because you just take the percent numbers and plug them right in. If you are so inclined, you can convert the percent to a decimal, which would mean moving this over 2 places to the left, then you don't need the 100. But if you don't want to be thinking about extra things, because there's a lot to think about, obviously, with the Chem Regents, just take the information, plug it in. When there's a percent, make sure that there's a division of 100. So that leads us to the end of the review of the notes, if you will. Let's go through some examples of some problems that we may come across. And I am seeing some people have joined as we've been talking, and again, I will do my best to get to those questions. I believe we'll be able to because we're doing pretty good with time. I hope I'm not going too fast for you. Okay. So let's look at, give me a second here. Okay, so we're going to go back through here. My apologies, I am switching. Okay, here we go. All right, so we're now looking at some basic Regents questions. Now it says here, base your answers to questions 1 through 3 on the information below. So if you're going to try and do these along with me, It would be good to have a calculator out if you haven't already gotten one out, and your reference tables, just so that you can look at some things as I'm referring to it. Now, let me just put this screen up here. Okay, so this gives us the means to now right on top of this. Now, it says the element boron has a trace element in the Earth's crust, is found in foods produced from plants. Boron has only 2 naturally occurring stable isotopes, boron 10 and boron 11. Now, question number 1 says, state in terms of subatomic particles one difference between the nucleus of a carbon 11 atom and the nucleus of a boron 11 atom. So in order to answer this question, we can see that they're clearly 2 different elements. If they're 2 different elements, right off the bat, you know that their proton number must be different. And that's one of the subatomic particles, like I told you earlier, that is going to be different. Since their proton number is different, but they have the same mass number, that would also indicate that their neutron number is different. So you can go so far as saying that they have different proton numbers, or they have different neutron numbers, or you can even start to figure out what the actual numerical difference is. It is not necessary, however, to do that, but we should understand that boron, if we look on our periodic table, which I am currently looking at, boron has an atomic number of 5, carbon has an atomic number of 6. That would let us understand that carbon has 1 more proton than boron. If we wanted to be specific about the neutron number, we could say that boron has 1 more neutron than carbon. Now, if we look at the next one, it says, write an isotopic notation of the heavier isotope of the element boron. And your response must include the atomic number, the mass number, and the symbol. So if we look at this, and I'm going to write it down here, obviously we have to do, let's try it again here. My apologies. Okay. Okay, so here's our symbol boron. And when we talk about the atomic number, we simply have to look at the periodic table. There's your 5. And then since they're talking about the heavier one, obviously we're going to go for the isotope that has the bigger mass number, which is 11. And simply doing that, and pardon me because I do have sloppy penmanship, that would be the answer you're looking for, and that would give you the credit. Okay, so let's clear that. Now, question 3 says, compare the abundance of the 2 naturally occurring isotopes of boron. Now, when we look at this, we can see that there's boron 10 and boron 11. So really what they're looking for you to tell them is which one is more abundant or which one is less abundant. Now, from the information given, it's not enough for you to be able to answer the question unless you look at the atomic mass of boron on your periodic table. So if you have the periodic table, take a look at it. It is 10.81. And when we talk about a question that's comparing abundances like this question, we look at the isotope that has the larger mass number. I'm sorry, we look at the isotope that has the mass number that is closest to the element's atomic mass found on the periodic table. In this case, it is the isotope with the larger mass number, which is boron 11. And since that element has a mass number that is closer to the atomic mass of boron on the periodic table, we can easily say that boron 11 is more abundant, or we can say boron 10 is less abundant. All right, let's exit this screen for a second, and then we're going to go on to some other questions. Okay, so here we're looking at base your answer to questions 4 through 6 on the information below and your knowledge of chemistry. And just as a side note, I know we all live in the fast lane and you guys are busy, and this is probably going to be your last Regents, and you are going to be thinking about getting the Regents done. Please take the time to read directions, okay? It takes an extra second, and sometimes there's information in there that actually is going to be important for you. Same thing with the little paragraph like this. So it says the Bohr model of the atom was developed in the early part of the 20th century. A diagram of the Bohr model for one atom in the ground state of a specific element is shown below. The nucleus of this atom contains 4 protons and 5 neutrons. So it says, using the Bohr model, describe the changes in electron energy and electron location when an atom changes from the ground state to the excited state. So now we're looking at the ground and excited state question. So here they want you to say, what is the change in electron energy? So when it's going from ground to excited state, you simply have to say the electron is gaining energy. That's all you have to say, or energy is absorbed. When we look at the second part of the question, it says, what is the change in electron location? Clearly, if it's getting excited, it's jumping to a higher level. So you could just say it's going to a higher energy level, or it's going to a higher shell. It's going further from the nucleus. And just as a side note, as electrons get further and further and further from the nucleus, although they all are the same electron, the further they are from the nucleus, the more energy they actually have to possess in order to maintain their location. So that's a simple question. Now it says here, state the number of electrons in each shell in this atom in the ground state, the number in the first shell, the number in the second shell. Now if we look at this particular question here, we can see that it's telling us there are 4 protons and 5 neutrons. So 4 protons is telling us the atomic number. And that atomic number is for beryllium. It's atomic number 4. And we could simply look at the periodic table and we can see that there are 2 electrons in the first shell and there are 2 electrons in the second shell. Now, just as a side note, and I like to do side notes, if you recall, you may have learned a formula called 2n squared. 2n squared is the way to figure out the maximum number of electrons that would occur or be found in any particular shell. So if we talk about the n representing the energy level, if it's the first shell, 2 times 1 squared is 2. If it's the second shell, 2 times 2 squared is 8. If it's the third shell, 2 times 3 squared is 18, and 2 times 4 squared would be 32. So this is just a simple way to remember the maximum number that you would find in any shell. Not to be confused with valence electrons, which is always going to be 8. Now the last question says, state the atomic number and the mass number of this element. Well, we already figured out that its atomic number is going to be the same as the proton number. And if we talk about the mass number, the mass is going to be protons plus neutrons, which is 9. So for our answers here, atomic number would be 4, mass number would be 9. So I hope you're seeing there is a simplicity here. And as I have been telling my students all year long, chemistry is easy. You can do it. So don't give up and try not to stress, because you probably know a lot more than you give yourself credit for. Now let's look at some classic multiple choice questions. And if we talk about this, we can see question number 7. What is the number of electrons in a potassium atom? Now, what we can understand from this question is the word atom is a significant word in this question, because if it's an atom, we know that electron number is going to be the same as proton number, which is always going to be atomic number. So we simply look on the periodic table and we can see that this is going to be your answer, choice B, 19, because atomic number is going to be 19. And since 19 is the number of protons, and again, that's the significant word there, atom. If it said ion, then it would be +1 ion, it would be choice A. But for this question, it's choice B. Question 8, which phrase describes the charge and mass of a neutron? So when we look at this one, we simply, if we forget, we can go to table O. But when we talk about the charge and mass of a neutron, we know that a neutron has no charge, but we know that it does have a mass, and that's why it's going to be choice D. So if we talk about its notation, and I'll just write over this, there's your neutron with a mass of 1 and a charge of 0, and that's going to be found on table O. Question 9, which substance cannot be broken down by a chemical change? And when we're talking about this kind of question, we're really looking at, or the Regents, I should say, is really checking to see that you recognize that elements cannot be broken down chemically. Compounds can be broken down into elements, but once we're broken down into an element, we cannot get broken down any further. And ammonia, propanol, and ethanol are all examples of compounds. Zirconium is the only one that is an element, and that would be your correct answer there. Question 10, what is the overall charge of an ion that has 12 protons, 10 electrons, and 14 neutrons? So this is a great question because now it's checking your understanding of the subatomic particles that make up an atom or an ion. Now, since they're telling you that it has 12 protons, they're telling you that it is element number 12, which is magnesium. But you don't need to look at the periodic table to answer this question, because if there's 12 protons in the nucleus, and we have 10 electrons outside the nucleus, there's a difference of 2 there. And since it has 2 less electrons, we would understand that this is going to be a +2 charge. The neutron number in this particular question is really information that you don't need to know. And sometimes they will throw information into a question that may not necessarily be needed. Let's look at question 11. Which statement describes the distribution of charge in an atom? So remember, you have 3 subatomic particles. You have a proton that's positively charged, that's in the nucleus. You have a neutron that has no charge, it's also in the nucleus. And then you have electrons outside the nucleus, which are negative. So we want to look at these answers. And if we look at the first one, a neutral nucleus, well, that already can't be true because a nucleus is always going to be positively charged. So choice A and B are off the table. And when you're going through the multiple choice questions, if you know an answer is definitely not right, just put a line through it. It gives you a little bit more power and confidence as you progress through the exam. So now we're narrowed down to choice C and D. So a positively charged nucleus is surrounded by 1 or more negatively charged electrons. That is your correct answer. If we look at choice D, why is it incorrect? Because it's saying a positively charged nucleus is surrounded by 1 or more positively charged electrons, and we know electrons don't have a positive charge. Choice D would be your answer there. All right, let's go on to question 12. The atomic mass of magnesium is the weighted average of the atomic masses of, and this goes back to the example I talked about before, of the, if we look at this, all of the artificially produced isotopes of magnesium, no. All of the naturally occurring isotopes of magnesium, yes, this is true. The 2 most abundant artificially produced isotopes of magnesium, no, because just by saying the 2, we're limiting, we don't know how many isotopes there are, and the 2 most abundant naturally occurring isotopes of magnesium. So when we look at this, it's not about artificial, because that's a nuclear situation. It's always about what's found in nature. So choice B would be the correct answer. Do not be fooled. There's other versions of this question where they say the weighted average of the atomic mass of the most abundant. And that was the example I talked about before. It can't be the weighted average of the most abundant because that would only be 1 isotope. You can't average 1 thing. So we want to understand that it's always all of the isotopes. Let's look at question 13. The numbers of protons and neutrons in each of 4 different atoms are shown in the table below. So when we look at this, we have atoms A, D, E, and G, their proton number, their neutron number. Which 2 atoms represent isotopes of the same element? So in order to navigate your way through this, you have to look for the 2 that have the same number of protons, because if they're the same element, they must have the same atomic number, which means they must have the same proton number. And these are the only 2 that have the same proton number. So this would be your correct answer, choice C, which would be atoms E and D. Which atom in the ground state has an outermost electron with the most energy? So this goes back to what I was talking about before. The atom, the electrons that are furthest from the nucleus are going to be the ones that possess the most energy. And if we look at this, we can see that lithium is in period 2. It only has 2 shells. Sodium has 3 shells. Potassium has 4 shells. And cesium has 6 shells. So what we can understand is the correct choice is going to be cesium, because those are the atoms that have electrons that are furthest from the nucleus. Therefore, those electrons will have the most energy. And you'll notice these are all group 1 metals as well. Question 15. Which electron configuration represents an atom of magnesium in an excited state? To navigate your way through this question, you need to look at your periodic table, and you need to look at what the electron configuration is for magnesium. Because on the periodic table, that would represent the ground state. When we try to determine which answer is going to be the excited state, it must have the same amount of electrons, just a little redistribution of them. Choice C is showing us what the representation for the electron configuration would be in the ground state. This is what you see on the periodic table. Notice that it has 12 electrons. Choice A would be the only other one that also has 12 electrons, but notice 1 electron from the second shell jumped up to the third shell. These two would not be correct because there are too many electrons there. Okay, here's a bright line spectra question. The diagram below represents the bright light spectra of 4 elements and a bright line spectrum produced by a mixture of 3 of these elements. So here are 4 elements, and then here's the mixture. It says which element is not present in the mixture. So when we talk about an element, any one particular element being present in the mixture, every line for that element must be present in the mixture. If every line is not present, then we can understand that it's not going to be present. You can't have some of the lines for an element in the mixture and say the element is there. Every single line must be present. And so basically all you're doing is lining up and comparing. And if we look at element X, we can see that these 2 lines do not appear in the mixture. And because these 2 lines don't appear, even though some of the other lines do, we can understand that X would not be present. So keep in mind, it's all the lines or else it's not present. Let's look at some other questions here. In the wave mechanical model of the atom, an orbital is defined as, and again, it's about electrons. So choice A is saying a region of the most probable proton location. No good. And choice C is also talking about protons. So we can eliminate choice A and C right off the bat. When we look at choice B, it says a region of the most probable electron location, which is the correct answer, because we must keep in mind that when we talk about electrons, we can never know exactly where they are going to be located, which is why choice D is not correct. 18 and 19 are looking at Lewis dot diagrams. So it says which Lewis dot diagram represents a nitrogen atom in the ground state. To do these correctly, whether it's a multiple choice or a free response question, you need to know how many valence electrons a nitrogen atom has. So a nitrogen atom, if we look on the periodic table at its electron configuration, we notice that it has 5 valence electrons. So you simply look for the choice that has 5 electrons in it, or 5 dots. So here we have our 5 dots. Choice C would be a correct answer. So if they ask you to draw a Lewis dot diagram or an electron dot diagram, please be sure that you put dots in there. A structural formula, if we're talking about a molecule, would not necessarily have to have the electrons in there if we're talking about a compound or a diatomic element. But when we talk about a dot diagram, the dot is a dead giveaway that dot should be present. And keep in mind, we can only have 2 dots, a maximum of 2 dots on any one particular side. Now here it says which Lewis dot diagram for the final question represents a fluoride ion. And what we want to understand first is how many electrons, how many valence electrons does a fluorine atom have, which is 7. And since it's an ion that forms a -1 charge, it's going to be adding 1 electron, giving us a total of 8. That narrows it down to these 2, but keep in mind, if it's an ion, you have to bracket and you have to put your charges in there. Okay, so that brings us to a conclusion of the review questions here. And what I'd like to do now is try and address some of the questions that I see were submitted for the through the Remind. So just give me a moment here to get rid of this. I'm going to get rid of that. There's my daughter. Okay, nope, that's not it. Sorry about that. Let's go back to here. Okay. Hi, it's me. Okay, so what I'm going to do is use this feature where you're going to see, for me to answer questions, if I have to write, I'm going to put something like this up, which is basically going to be a whiteboard where, look, I can write. Okay, so if I disappear for a moment, don't be nervous. Look, it's Dr. Shanzer. Okay, so let's look at some of these questions here. And I appreciate you guys taking the time. So let's see here. From Caitlin, how do you make an electron dot diagram for CH3Br? So this is really an organic question that will be addressed during the organic section. But if we look at this, I can quickly kind of go through it. So CH3Br. So the first thing we have to know is the total amount of valence electrons. So carbon we know has 4. We know hydrogen has 3. And we know bromine has 7. So when we look at our final diagram, we should end up with 14 electrons. So let's look at how we're going to do this. Let me erase that. So carbon is always going to be in the center, and then we're going to build our molecule. So let's put our H's here. Pardon my handwriting, it's very sloppy. And then here's our bromine. And remember the octet and duet rule. So if we think about that, hydrogen, remember each bond line represents a pair of shared electrons. So if we look at hydrogens are all happy because they all have their duet. Carbon has 4 bonds, which represents 8 electrons, but bromine does not. So if we complete bromine's octet, which I don't know if you can see that here, let's see. These are representing electrons. We can see that bromine has an octet around it as well. So if we finish and we count up, we can see that we have, with bond lines, we have 8 electrons plus the 3 pairs of 6 electrons, and that will give us your total of 14 electrons. So if you follow the octet and duet rule, you will always end up in the right place. And I hope that helped. So let's look at the next one. I'm going to get rid of that screen. It's me again. Okay, Caitlin had another question. Will you be given the isotope of an element? If not, where would you find them? So basically, if they give you the notation of a particular element, and we'll go back to the whiteboard again for a second, and you can look at the examples that I gave you in the notes. Here is one isotope of sodium. Now, if we get rid of this, and I write 21, there's another isotope of sodium. So they may ask you to differentiate between them through certain pieces of information that they give you. So I wouldn't worry too much about that. You'll get what information you need from that. Can you explain when to use gram atomic mass, gram formula mass, gram molecular mass equals molar mass? Okay, so when we talk about gram formula mass, or GFM, which will be covered in the math of chemistry unit, we can understand that you're simply looking at the atomic mass for every atom that is being represented in the compound. So if we talk about, here, let's go back to the whiteboard again for a second. If we talk about, let's say, H2O, okay, if we look at, we can see that hydrogen, there are 2 hydrogens. So that's going to be 2 times 1, that gives you 2. And then if we look at oxygen, there's 1 oxygen, so that's going to be 1 times 16, because we're going to round. So that's going to give us 16. And when we get our GFM, or formula mass, or molar mass, it's going to be 18.0, and it's going to be grams per 1 mole. Okay, so I hope that helped you. Let's clear that off. Erase, okay. Let's see. Are you going to answer the questions that people texted? I guess you can see by now that that actually is going to happen. So we are closing in on the end of this broadcast, and I hope it was helpful for you. That seems to be all the interest that people have in terms of submitting questions. So I will bid you a good day. Keep up the good work. Remember, chemistry is easy. You can do this. And remember to use your reference tables. Check them because they're very helpful, and there's a lot of information on there that is being given to you to make it easier for you to navigate your way through the questions. Good luck with everything. Thank you for watching, and have a good day. Bye-bye.